Okay. Bismillahirrahmanirrahim. So in the last class we did stop over here the graph for the different types of relations. Okay, we can draw the graph for the relations. For example, for reflexive relation, every node or every vertex here has a loop, because reflexive relation, it means it has the same in elements. For example, the 1 comma 1, 2 comma 2, 3 comma 3, that is called a reflexive relation. And irreflexive, there is no looping. So any relation without looping is irreflexive. Symmetric is if there is a if there is an element A to B, then there should be a B to A. It's called symmetric. And antisymmetric is there is no bidirectional. It means if there is A to B, then there should not be B to A. That is called antisymmetric. What we discussed in the last class. Moving ahead, closures of relations. Here we are going to study about the reflexive closure and symmetric closure, transitive closures. Three closure we are going to study over here. Starting from the reflexive, first we will see what is closure. For any property X, the X closure of a set A is defined as a smallest superset of A that has given property. The smallest superset of the given set A. Okay. The reflexive closure of a relation R on A is obtained by adding A to R for each A belongs to the set A, which is not in A. So what is reflexive? For example, if we talk about the reflexive for the integers 1 comma 2, the reflexive relation for the set A for the elements 1 comma 2, what we have? 1 1 and 2 2. Okay, now here in the closure reflexive, for any relation with R on a set A is obtained by adding these 1 1 or 2 2 or any element, okay, its element for each A which is belonging to the set, okay, which is not really in the R. So for example, let us take R is the relation 1 1 1 2 2 1 3 2 on the set 1 2 3, okay, and it is not reflexive. So how to make it reflexive closure? That is, you make this set as reflexive, okay, by adding the elements which are missing. So if you take this set 1 1 1 2 2 1 3 2 on a set, or this relation on a set 1 2 3, so which are the elements which are missing in the relation R to make this R reflexive? 3 3 and 2 2. So we are going to add to this relation, that is 1 1 1 2 2 1 3 2. Now what are the missing? We are missing 2 2 and 3 3. Now this becomes the reflexive R, reflexive closure R. 2 3, this is not reflexive. Reflexive ايش القاعدة حق reflexive؟ القاعدة reflexive إذا في عندك السيت مثلا A set عندك elements 1 2. So ايش reflexive relation حق 1 A؟ هي لازم هيكون 1 1 و 2 2. ما في مشكلة إذا في ولا ما في ما في علاقة. فهذا لازم هيكون 1 1 2 2. This set does not have 1 1 2 does not have from this set, okay, there is missing 2 2 and 3 3. So you add this to make this as reflexive closure. There is another example for A comma B where A is less than B. So the reflexive relation is you union this with A comma A where A belongs to the Z. Z is set of integers. A belongs to the set of integers. Then which is A comma B where A is less than or equal to B. Because you see A both are equal and AB one is less than. When you union less than union equal, what you have? You see this is less than union with equal. Sorry, this AA. So you have A less than B and A equal to B. Then if you union these two, what it is? Less than or equal to B. So this is a closer relation, which is this one, A comma B, such that A less than or equal to B. Then symmetric closure. What is the symmetric rule? If there is a element 1 comma 2 in the relation, then there should be element 2 comma 1 in the relation, right? This is symmetric. This is the rule for the symmetric. So for example, if there is A comma B in general, then there should be B comma A. Now symmetric closure R is obtained by adding B comma A for every A comma B in the relation. So you are going to add B comma A. So if R has A comma B, then B comma 1 is R inverse. I'll X here, B comma A. So you are going to do union R inverse. إذا عندك A comma مثلا عندك 1 comma 2, then there should be 2 comma 1. So for example, this is the relation given on the set 1, 2, 3. Now what are the elements which are missing to make this a symmetric closure? 2, 1 and 1, 3, because there is a 1, 2, but there is no 2, 1. There is 3, 1, but there is no 1, 3. There is 2, 3, there is a 3, 2. Okay, so we are missing is 2, 1 and 1, 3. So we add 2, 1 and 1, 3 to make it symmetric closure. This is another example. Now moving ahead to transitive closure. In transitive, what is the transitive rule? What is the transitive rule? If there is a relation, if there is an element A comma B and B comma C, then there should be A comma C in the relation R. Okay, so here this is obtained by adding A comma C for every A comma B and B comma C. For each A comma B and B comma C, we need to add A comma C. So it is something like R composed of union of R power n, where n belongs to the z positive integers. I mean, n belongs to the positive integers. It means we'll take an example to understand this. If this is a relation on the set 1, 2, 3, it has 1 comma 1, 1 comma 2, 2 comma 1 and 3 comma 2. Okay, now to make it transitive, what we'll do is we'll count the number of elements in the set. We'll count the number of elements and we are going to union these. Example, R star is R union R square union R cube. Okay, to add the A comma C in this one. Okay, for example, over here we have the R. Okay, we are going to do R is present, R square. R square is R composed of R in transitive. Okay, so 1 comma 1 will come, because if there is a 1 comma 1 and then again 1 comma 1, so it will come 1 comma 1. Now if there is a 1 comma 2 and 2 comma 1, then it is 1 comma 1, it will come again. Okay, now if there is 1 comma 1 and 1 comma 2, so you will get 1 2, so 1 2. Clear? It's not clear. Now what is transitive property first? If there is AB, BC, then there should be AC. We are going to add the missing AC for AB and BC. We are going to add the missing AC for AB and for each AB and BC. Clear? Now what is the rule is that it is something like union of r power n, where n belongs to the positive integers. N is number of elements in the set. N is the number of elements in the set. Okay, now here let us take R. This is the relation given 1 1 1 2 2 comma 1 3 comma 2. Okay, now here what is missing for us? If there is 1 comma 2 and 2 comma 1, there should be 1 comma 1. Okay, but if there is 3 comma 2 and 2 comma 1, there should be 1 comma, no, there should be 2 comma 1, 3 comma 1, sorry, there should be a 3 comma 1, right? 2 comma 2, there should be 2 comma 2 also. No, we take the A and C. We take A and C for every A, B and B, C. We are going to take A and C. Yeah, this should be 3 comma 1. This is A, this is B, and this is B, and this is C. 3 comma 1. That should be 3 comma 1. Okay, this should be added 3 comma 1. Now here how to add these values? Okay, the basic rule is you calculate the R star. R star is nothing but union of the relations, okay, to the power of n, where n is the number of elements. How many elements you have here? 3 elements. So n is 3. You need to do the union of R cube.
Can't we take 1 comma 2 and 3 comma 2?
We can.
Why is 3 comma 1 not 1 comma 3?
What is required here? What is the rule?
A, B, C.
If there is A and B and B, C, then there should be A and C. We take the first element from the first and the last element from the second. فين البي؟ بي لازم يكون مشترك، بي يكون common. شوف إذا أنت أخذت A و B، فين البي دحين؟ B ممكن هذا B أو C، فممكن أقول 2 كما 2 لازم يكون 2 كما 2. إذا أخذت الإكزامبل هذول اثنين لازم يكون 2 كما 2. Clear? Now here, to get the complete solution, we have to do the union of R cube. So first you find the R cube. To find the R cube, what we do is we find R square and then multiply R square with the R. So we are going to do the composition. We're going to compose. Okay. Compose reflexive. Now here, R composed of R will give us R square. So R we are going to compose again with the same relation R. Composed with the same relation R. So if you do compose, we are going to talk about the reflexio. So definitely if there is a 1 comma 1, 1 comma 1 will come as it is. Then if there is 1 comma 2 and 2 comma 1, again 1 comma 1, which is already present. Okay, and then if there is 2 comma 1 and 1 comma 2, then you have 2 comma 2. So you have 2 comma 2. Then if there is 3 comma 2 and then 2 comma 1, so what you have? 3 comma 1. So you have 3 comma 1. This is your R square. For R cube is equal to R square composed with R. So now you do this composed with this R. So we are going to do now this one composed with this one. Okay. Now if there is 1 comma 1, yeah, it will present 1 comma 1. So it is 1 comma 1. Clear? And there is 1 comma 2, then there is a 2 comma 1. Again 1 comma 1 it is. Okay. It is 1 comma 2, then you have 2 comma 1. Then it is okay, 2 comma 2. 1 comma 2. AC. You take A and C. It is 1 comma 1, right? So you have 1 comma 1. Then if there is a 2 comma 2, then you have 2 comma 1.
كيف تمشي يعني؟ 1 كما 1 1 كما 2
The second one. Oh, I'm sorry. We are calculating about the R square. R square composed of, see, this is R square composed with R.
1 كما 1 1 كما 1
1 comma 1 is same. 1 comma 2.
In R2, in R square and R. 1 comma 1 is common, we write it?
Yeah, you write common or you can calculate it. It will come as it is. Even if you calculate, it will come as it is. 1 comma 2.
1 كما 2 1 كما 2
No, it should be A, B and B, C you have to take. And then you take AC.
A B and B C 1 كما 2
Yeah.
A B and B C
You take A, B and you take in the another relation what you have B here. For example, you have 2 B here. You take from there 2. 2 and the next number. So you take A from here and the third from C from here.
This one must be sequence. You can pick up instead of the first two elements.
No, it's not in.
Make the transport of the other one will take the second and third.
Yeah.
The important thing يعني مش لازم تتبع تكون يعني واحد يعني ممكن ترتيب تسلسل المهم انك انت تلاقي في عامل مشترك يعني هذا واحد اثنين ما يضبط خلاص اذا واحد اثنين اثنين واحد بعدين الواحد اثنين اللي فوق يروح مع حاجه ثانيه
Clear? So this is your R cube. If you go according to this rule, okay. So this R cube is what your R star is. Okay, union R cube with the all you union all these. Okay, you will get the R star. R union R square union R cube. Okay, all you have to do the common elements, bring all the elements together. The next, moving ahead to the equivalence relation. Now an equivalence relation on a set A is simply a binary relation on A that is reflexive, symmetric and transitive. In any set with any given relation on a set is said to be equivalence when it is reflexive. Reflexive should be true, symmetric should be true, transitive should be true. If these three properties are true, then we call that relation as a equivalence relation. For example, consider a relation of a comma b where a minus b is an integer. For example, if you take 2 and 3, okay, 2 and 3. So if you do 2 minus 3, what you get? Minus 1 is also an integer. Or you take, for example, 3 and 2. 3 minus 2, 1 is also an integer. So it should satisfy this condition. Then we have to prove reflexive, symmetric and transitive for this condition. That if you take a minus a and b, then a minus b should be an integer. If you take a minus b from any real number, then the result should be an integer. Okay. Now for reflexive is a looping. If there is one, there should be one common. If there is a in the set, there should be a and a, right? So if you take a and a comma a, then a minus a should be is always 0. If you take a is 1, a2, a3, a4, 2 minus 2 0, 3 minus 3 0, 4 minus 4 0. So 0 is an integer, right? 0 is an integer, then a relates with a for all integers or for all a. It's clear? This is reflexive. Clear? Moving ahead to the symmetric. What is symmetric? For if there is a comma b, then there should be b comma a. So if there is a minus b, a minus b is an integer, then b minus a should also be a integer.
3 minus 2 and 2 minus 3.
Yeah, for example, if you take a2, b3, so it is 2 minus 3 minus 1 is an integer, and 3 minus 2 is 1 is also an integer. So it is symmetric. So if you take a relates to b, then a minus b is an integer, then b minus b is also an integer. So we say that b relates with a. It is symmetric. Okay. Transitive. If a relates with b and b relates with c, then a relates with c. So it means that if there is a minus b is an integer and b minus c is an integer, then a minus c is also an integer. Okay. Now how to prove this transitive? So we'll take for transitive, we say the rule says that there should a minus b should be an integer. Okay. So for transitive, Okay. Now we are talking about the equivalence. Okay, I'll just repeat from the beginning. Equivalence, any relation is said to be equivalence if it satisfies reflexive, symmetric and transitive property. Okay. For any given relation, we are going to check these three properties. Reflexive property for the relation R, symmetric property for the relation R, transitive property for the relation R. If these three properties are satisfied, then we say that the given relation is a equivalence relation. Okay. Now let us consider an example over here. Show that a relation on the set of real numbers R such that a comma b such that a minus b is an integer. It means that if you take any two numbers, okay, then that the difference of these two numbers is an integer. For example, 2, 3, 4, 5, any two numbers. Now on this condition, we have to check reflexive for the set of real numbers. We have to check symmetric for the set of real numbers. We have to check transitive for the set of real numbers. Okay. Now given is the set of real numbers, and what it is asked here is a. The condition says that a minus b is an integer. If you take first reflexive says that for any element, so there should be the same element, okay, along with a comma a. So if you take the a, any integer a, then a minus the same a is always 0. If you take any integer, any number, 3, 4, 5, 6, 7, 8, 3 minus 3 0, 4 minus 4 0, then it means that a relates with a in this condition. So it satisfies the reflexive relation. Yeah, all the numbers are reflexive. Then second thing is we are going to check for symmetric. Symmetric, we check for symmetric. If there is a comma b, then there should be a b comma a. What's the condition is a minus b. If the a minus b is an integer, then b minus c a should also be an integer. Now if you consider any number, okay, b minus a for any number, for example 3 minus 4, a3 b4, 3 minus 4 minus 1 is an integer, and 4 minus 3 1 is an integer. Okay, now how do you prove this one is, if you take, if this is r and this r inverse, right, it's just an opposite way, b minus a. Okay, so if you take this one a minus b, okay, it gives an integer, then it is inverse of it, that is b minus a always a integer, it gives an integer. So we say that the a minus b relates with b minus a as a relation. Okay, then we say that it is a symmetric as given over here, b relates with a. Okay, now coming to the transitive. So transitive says that if there is a comma b and B comma C, then there should be A comma C. So if there is A minus B is an integer and B minus C is an integer, then A minus C is also an integer. We see that A minus C is equal to A minus B plus B minus C. How do we solve this? You take this minus B plus B out. What it is? A minus C, right? Right? If you take minus B minus B. So it means that A minus C is equal to A minus B plus B minus C, right? So you say A minus B as an integer, B minus C is also an integer. So A minus C as an integer, B minus C is an integer. The addition of two integers is an integer. Any integer plus integer is an integer by closure property. Hence, it satisfies A relates with C. So it is transitive. Hence, it is transitive. So this relation we say that is a reflexive relation. I'm sorry, equivalence relation. Clear? Clear the equivalence relation? So for any given relation, you have to check this equivalency. There are more examples over here. The second example on a set of integers show that R is an equivalence relation. R is given as A minus B AB, where A is congruent to B in the mode of M, where M is greater than 1. The congruency relation says that if you do A mod M should be equal to B mod M, or M divides A minus B. A minus B should be divided by M, must be divided by M. Okay, then we say that A is congruent to B. The congruency rule says that A is congruent to B in the mode of M if and only if M divides A minus B. Any two integer you take, the A minus B should be divided by M. This is congruency rule. Now based on this rule, you check for these numbers for the set of integers. Okay, you check the reflexive, symmetric and transitive. Okay, let us take the reflexive. It is always with a single number. Okay, it's a looping. We take A. So if it is A minus A, M divides A minus A. A minus A is always 0. 0 divided by M, it satisfies. Okay, 0 divided by M is again, it satisfies, it will divide by 0.
0
Yeah, 0. It will divide by 0. So it satisfies. Coming to the symmetric, if A relates to B, then M divides A minus B. Therefore, M divides minus of A minus B. That is the inverse of A minus B. Okay, it is sure. For example, let's say A minus B is 4 and M is 2. So 4 by 2 it divides 2 times. Let's say B minus A is minus 4 and Al here, opposite. Yeah, so it is minus 4. Minus 4 divided by 2 is again by minus 2, which is also an integer. So it satisfies the symmetric relation. Clear? All integers in this rule will come as symmetric. Symmetric and reflexive. We'll check for transitive. Okay? Transitive says that transitive, if there is A and AB and BC, then it should be AC, right? Okay? If M divides A minus B, and M divides B minus C, B minus C, then M divides A minus C. Okay, now you can prove again the same. A minus C is what? A minus B plus B minus C. Okay, so divide, if it is dividing by M and divided by M, you add these two. If you add these two, A minus C divided by M, right? So M divides A by C. Correct? So it satisfies the transitive property. Okay? So it hence this is equivalence relation. So hence it is equivalence.
Talking but it's just يعني مجرد عمليات بسيطة يعني هي كلام كثير.
هذا لازم تفهم العمليات بسيطة، لازم يفهم هذا الشيء.
يعني ليش العمليات طلعت هيك؟
ايوه، هو لازم افهم العمليات، هذا عمليات الريفلكسيو سيمتريك اند ترانزيتيف.
هذا هون نقطة يعني على شو بده يسألك واحد؟
هو أسألك أقول لك it will give this and ask you to show that this is equivalence. السؤال هذا السؤال الexample هذا السؤال A comma B such that A is congruent to B in the mode of M where M is greater than 1 on a set of integers. Z it means integers. Yeah, all integers. Now you have to prove reflexive, you have to prove symmetric and transitive. If these are true, then you say that this relation R is equivalence.
Then if they ask me satisfy your answer.
This is satisfaction. No, yeah, all of it. This you have to write this. Yeah, reflect, transitive, symmetric. Sorry, reflexive, symmetric, and transitive. This is your justification. Okay. So this is another example over here. I will skip this one. Now moving ahead to equivalence classes. Now we are going to talk about a set of the relations. Okay. Now let R be an equivalence relation on a set A, then the set of all elements that are related to the element A of the set A is called the equivalence class of A.
A is a number and set is A.
Yeah, capital A is set, small a is an element of set, and all the elements which are related with the small a, okay, we call it as an equivalence class of A. For example, let us set A is 1, 2, 3. Then all the elements related with the 2 on any condition, all the elements related with the 2 is called the set of the equivalence class of 2. Class of 2. For example, let's A is 1, 2, 3. Now here A is a set, capital set, and the element of A, for example, 2. Okay. Now all the elements which are related to 2. Any element on some condition, we write the relation based on some condition, right? All the elements related to 2 on that condition of the relation is called the equivalence class of 2. Equivalence class of 2. We'll take an example here to understand this. What are the equivalence class of 0 and 1 for the congruence modulo 4?
Elements have 0 or 1.
0 and 1. Elements of 0, 1.
Yes.
A is a set with 0, 1. The condition is congruence in modulo 4. So it means 0 modulus no a is equal to the element mod with 4 should get 0.
Why 0?
This one a is equal to 0 with mod 4.
Why 0?
Which one? We have to find the class of 0 and class of 1.
First
Two different elements. 0 is different, 1 is different.
we will try first at 0 and another.
Yeah, first we will calculate what are the related elements of 0, which is the equivalence class of 0 in the modulo 4. So you have to find all the numbers. If you do mod with 4, should give you 0. Okay. Now what are those numbers? If you do the modulus with 4, should give you 0.
Minus 4 minus 4.
You have to find this a. Okay. Now 0 mod 4. See, 0 mod 4 is 0, right? Now you have to find a mod 4. All the elements a which will give 0. So what are those elements will give me 0?
4 divided by 4 0.
4 mod 4 is
0.
it is 0.
Can I find the elements of A that's equal to
If you do the mod of 4, should be equal to 0.
A must be find the A
Yeah,
that called the model 4 equals
0. All the integers, all such numbers that if you mod with 4 should give you 0. What are those lot of numbers?
4 8
4, 8,
minus 4 minus 8
minus 4, minus 8,
16
16,
minus 16
minus 16, 12, 12,
minus 12
minus 12.
the models and they find the remainder.
Find the remainder. Modulus is find the remainder. The remainder should be 0.
The remainder.
24 20 minus 24.
So it is the multiples of 4. 0, 4, 8, 12, 16. The multiples of 4. And on the other side, minus 4, minus 16. This is the equivalence class for 0. Equivalence class for 0. That is, we call it as an A of 0 in the modulus of 4.
Now 1.
Now you come to the 1.
1
The element 1. Now 1 mod 4 is 1, right? So you find A such that when you mod with 4 should give you 1.
and when you divide the number with 4
The remainder should be 1. If you divide the number A by 4, the remainder is 1. That is, the A mod 4 should give you
3
1. No, 3.
3 minus 3 divided by 4 1
3 divided by 4 is 1.
yeah
Where are you? 3 divided by 4 is
4 divided by 3 1 the remainder 1
not divide by 3, divide by 4.
then 3 divided 1 by
5 divided by 4, what is remainder?
1
1. This is the element. So you find the number A such that you get the remainder 1. You are not going to divide any number A by 4 by A. You are going to do A by 4. A divided by 4. So you give the list of those numbers whose remainder will be 1.
4 9
4 is 0. 4 you will not get.
5
5,
6.
9. 6 will give you 2.
13
7 will give you 3.
13
13, 17.
17
Yeah. So this list, this list 1, 5, 9, and on the other side -3, -7, -3. If you are doing minus modulus, what it is? If you do the minus modulus, you don't know how to do the modulus with the minus value? Yeah. What how to get the remainder of it? For example, -3 modulus 4, how much?
3 minus 4. The
4 minus 3.
Yes.
See, if you want to calculate, I'll just give an example here how to calculate the minus modulus for any minus value. Okay? For example, let us take 4. Mod 4 with any minus value. For example, -7. Okay? No, it will not give you 3. It will give you 1. How? You take the table of 4. 4, the next number is 8. The number which is greater than, just write greater than this number. That is 8, right? You do 8 minus 7. What is remainder? 1. This is the...
Then -5 mod 4 will give you...
No, -5 mod 4 will give you 3.
3, so 8 minus 5.
Yeah.
-2.
-3 mod 4 will give you... Because the next nearest number is 4. So 4 minus 3 is 1. Like this, if you have, for example, -11 mod 4. 12 minus 11, 1. Okay. So this is the equivalence class values for the element 1. So this is how you calculate the equivalence class. The question is this one. It will give you what is the equivalence class of the element on the condition. Then the next is partitions. Partitions of the equivalence class.
تركز على الناتج بس من السؤال، وده تسمى المود بالعكس.
Okay. The next is partitions. A partition of a set S is a collection of disjoint non-empty subset of S. For any set S, partitions are nothing but dividing that set. If you union again those partitions, you will get the set. Okay, for example, here the given this is a set, okay, called set A. Now this set A you make partitions. For example, this is A1, A2, A3, okay, then A4, A5, A6, A7, A8, these partitions. So if you combine all this, if you do union of all these partitions, you will get again A. This is called partition. Okay, so how we represent the partition is A of I, where I belongs to the capital I. Capital I is the index of the set A1, A2, A3, A4, A5. Okay, when you do this A1 union A2 union A3 union A4, you will get A. Okay, and when you do the intersection, A1 intersection A2 is null. There is no common element between two partitions. There is no common element between two partitions. For example, if you want to do the partition of the set Let's say this is a set and you have the elements 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now it is a set A. If you do the partition of it, for example, I'll do this as one partition, this as partition 2, this is partition 3, this is and this one partition 4. So it is A1, A2, A3, A4. If I union all this, A1 union A2 union A3 union A4, I will get A. I will get 1, 2, 3, 4, 5, 6, 7, 8, 9. If I intersection any two partitions, if we give you null, yeah, for example, if I A1 intersection A2, what it will give me? What is the common element between A1 and A2 is null. Okay. Now here example, the question is what are the sets in the partition of the integers arising from congruence of modulo 4? Congruence of modulo 4, it means the remainders are when you divide with the 4. If you divide 1 with the 4, what is the remainder? If you divide 1 with the 4, what is the remainder? 1 divided by 4, what is the remainder? Remaining. 1 modulus 4 is 1. What is the problem? In the previous slides you say okay, the next slide you are confused. 1 modulus 4. No, I am asking about the remainder. Will 1 divide by 4? It cannot be divided. So remainder is 1 only. 2 modulus 4 is 3 modulus 4 3. 4 modulus 4 0. So what is the modulo of 4 is 0, 1, 2, 3. Okay. Now what are the equivalence class of 0? 0, 4, 8, 12, 16. The equivalence class for 0. The equivalence class for 1, 1, 5, 2. 2 will give you 2 again. The equivalence class for 1. What is equivalence class for 1? We don't know. Just now we took before in this slide the equivalence class for 0 and 1 in the modulo of 4.
Okay.
1, 5, 9 in the equivalent modulo of 4. Okay. Then in the modulo of 4 the equivalence class for 2 is, if you divide the number you should get 2. 2, 6, 10, 14, 18 and all. And for 3, yeah, 3 divided by 4 remainder 3, 7, 11 and so on. Okay. So this is the classes. These are the partitions of integers coming from the modulo of 4. Okay. Go ahead, please. No, go ahead, please. No. You go ahead. It will be clear for others also. Modulus.
For me, and you explain it like 10 times for me, and I really didn't understand.
What you want to understand? Modulus? How to find the modulus?
Yeah.
Modulus is a reminder.
Okay.
If you want the modulus of 4 for a remainder, divide the number by 4 and what is remaining is the modulus of the number.
Okay. The question give us the model.
The modulo of 4 for example.
4.
Okay.
Then how Can I find مثلا 7 model 4?
7 modulus 4 is divide 7 by 4.
Yeah.
Okay. And then what is remaining? If you divide, it will go one time.
Yeah, 3.
3 remaining. So 3 is the modulus. 7 by 4. The remaining is 3. So modulus is 3. Modulus is nothing but, or modulo is nothing but the remainder of a number when you divide by any number.
When he said model a number,
Hmm.
then give me the reminder.
Yeah, you should take the reminders. For example, in this question, it is asking what are the set in the partitions of integers arising from congruence modulo 4. And what is the set? If you mod with the 4, okay, what the numbers you will get? Any number. We start from 0. If you do 0 modulo 4, 0 divided by 4, remaining is 0 again.
0 because
You cannot do it is 0 times remaining 0. Clear? We want to calculate the modulo of 4. We start from 0. 0, 0 divided by 4, it goes 0 times remaining 0. Right? This is the remainder 0. So 0 is 1 element in the set. Okay? The next 1. 1 divided by 4, it will not divide, the remaining is 1 only. It is 1. 2 divided by 4, it will not divide, the remaining is 2 only. So it is 2. Then 3 divided by 4, it will not divide, remaining is
0.
so you tell me 3 divided by 4, it will not divide, remaining is 3 only. The next is 4. 4 divided by 4, it divides one time, remaining is 0. 0 is already present here. Sorry.
For example, if 5 divided by 4, 1.
5 divides by 4, it goes one time, remaining 1.
Like subtraction, when we subtract 5 with 4.
You can make a subtraction with the 4, but if you make subtraction as for minus, we did, it is like it is same thing. 5 divided by 4, how many times it will divide? It will divide one time. What is remaining? 1 is remaining. So 1 is already present in our set. The set is 0, 1, 2, 3. Even you take 6, 6 divided by 4, it will divide one time, remaining 2, 2 is present. 7 divided by 4, it will divide one time, remaining 3, 3 is present. 8 divided by 4, it divides 2 time, remaining 0. You will get again 0, 1, 2, 3 only.
Then you stop when you get reminder 0, you stop here, then because it will repeat.
Yeah, it will repeat again the same. For the integers, it will repeat again. Okay. So this is the set. Now you want to calculate the partial sets for these 0 modulus with 4, you get 0. 4 modulus with 4, you get 0. 8 modulus with 4, you get 0. All the numbers, if you do the modulus, you will get the 0. So you get for 0, 4, 8, 12, or you get for 0, minus 4, minus 8, minus 12, and so on. And all the partial set for 1. If you divide 1 by 1, 5, you will 5 modulus 4, 1. Then 9. 9 modulus 4, it goes 2 times, remaining 1. Okay, 13, and so on. Clear? Then here minus 3, minus 7, and so on. Okay. Then over here, what are the numbers? If you do modulus, you get 2. It is 6. It is 10, 14. Okay, and so on. And here it is minus 2, minus 6, minus 8. No, sorry, it's not minus 8. Minus 10, and so on. Minus 6, if you do 8 minus 6, 2. Here 6. 6 divided by 4 is, what is the remainder? 2. 6 divided by 4, remaining is, it goes one time, remaining 2. So like this you find the class of 3. The class of 3 is, we have 7, 11, 15, and so on. Okay. In the same fashion, the class of minus 3, it is minus 1, 4 minus 1, 3. Then minus 5, 8 minus 5, 3. Minus 5. Okay. And so on. Minus 5, minus 9, and it continues. Okay. So this is what the answer for this question. As you see over here, this is the partial sets. The next, partial ordering. A relation R on a set S is called partial ordering of, or a partial order if it is reflexive, antisymmetric, and transitive. Now here it is same as equivalence, but here what we check is antisymmetric. We check reflexive, we have to check antisymmetric, and we have to check transitive. Then it is called partial order. That relation is called as a partial order relation. What we did for equivalence relation, we check 3 things, right? What are those 3 things? Reflexive, symmetric, and transitive. Now here we have to check for partial ordering set or a relation, we have to check reflexive, antisymmetric, and transitive. Again, reflexive is A comma A. If there is A, there should be A comma A. And antisymmetric is, what is antisymmetric? If there is A comma B, then there should not be B comma A. This is antisymmetric. If there is 1 comma 2, there should not be 2 comma 1. Okay. And transitive, the same thing. A comma B. If there is A comma B and B comma C, then there should be A comma C. A comma B, B comma C, then it should be A comma C. Now this you have to check for the given relation R on any set. If these 3 properties are satisfied, then that relation is called it as a partial order relation. Partial order relation. For example, show that the greater than or equal relation is a partial ordering on the set of integers. Now you try to solve this one. I don't know. If there is a time, then definitely. What can I do? Anyhow, we'll see, inshallah. I'll try to cover up as soon as possible, and we'll discuss, inshallah. Now, greater than or equal relation. So, on set of integers, greater than or equal to. Now, you check reflexive, antisymmetric, and transitive. Reflexive, antisymmetric, and transitive. Okay, on greater than or equal to, on set of integers. On set of integers and a set of numbers. Okay. Now, first of all, reflexive is if there is A, there is A comma A. So if you take any integer is equal to that integer. So or equal to, it satisfies. Right? A is greater than or equal to A. 2 is greater than or equal to 2. This is true, right? 3 is greater than or equal to 3. So it is right. So we say that this is a reflexive. Greater than or equal to relation is reflexive. The first condition is satisfied. The second condition is antisymmetric. Yeah, which is not symmetric. Antisymmetric, what we have to check is if there is A comma B, there should not be B comma A. Okay, on the condition if A is less than or equal to B, then B less than or equal to A is not true, right? For example, you take A1, B2. 1 is less than or equal to 2. It is not symmetric. It is anti-symmetric. I'm sorry. A greater than or equal to B, then there should not be B greater than or equal to A. If let's say A is 2, B is 1. 2 is greater than B, right? This is true. 2 greater than equal to 1. Is 1 is greater than or equal to 2? This is false, right? It means it is anti-symmetric. Hence it is anti-symmetric. A is greater than or equal to B, then and B is greater than or equal to A. Okay, it is not true. So it is anti-symmetric. Then finally you have to prove transitive. Transitive, what you have to prove? If you have A comma B and B comma C, B comma C, then there should be A comma C, right? So if there is A greater than or equal to B and B is greater than or equal to C, then A is greater than or equal to C by closure property, right? Akid. You take any number for this.
1, 2, 3.
No, you take 3, 2, 1. A is 3, B 2 and C 1. Now A greater than or equal to B. 3 is greater than 2. Right? And B greater than C. 2 is greater than 1. Then A greater than C. 3 is greater than 1. True, right? So hence it is transitive. You cannot have A3, B3, C1 because A is different than B. A is different from B. Okay, so it is transitive. Then we say that the greater than or equal to is a partial ordering set of integers. We also call it as a poset. Partial ordering set. Partial ordering set. Okay. So we'll stop here. We want to discuss some TMA. Okay. Okay, then we'll continue this one so that it will be clear for you. Okay, then here is a comparable definition for comparable and incomparable. Whether two elements are comparable or not. We can compare two elements from a set or not. Okay, so the elements A and B of a partial ordering set S comparable are called comparable if A relates with B or B has a relation with A. Okay, when A and B are elements of S such that neither A nor A relates with B or nor B relates with A, and A and B are incomparable. When these two has a relation, when AB has a relation and BA has a relation, and or BA has a relation, okay, then we say that A and B are comparable. We can compare A and B. And if there is no relation between A and B and there is no relation between B and A, then we say that A and B are not comparable or incomparable. Now what you say about the comparable? Comparable, it means we can compare two things. Okay, for example, I can compare a student with another student. This is good student, this is bad student. If they have the relation, they are in a one set, they have a relation, we say that it is comparable. Okay, now if they don't have a relation, I cannot compare a student with an employee or a teacher. I cannot compare a student with a teacher, so we say that a student and teacher are not comparable, incomparable. They don't have any relation. Okay, in the same set. Okay. Now for example, the partial order set on the set of positive integers on the division is 3 and 9 are comparable because 9 can be divided by 3. Okay, 3 and 9 comparable on the division of set of integers, that is 9 by 3. You can divide this one, so we can compare 3 and 9 because it is in the same set of the multiples of 3. Whereas we cannot compare 5 and 7, it is an incomparable because you cannot divide 5 by 7 nor you can divide 7 by 5. Both are wrong. If any one is true, then we say it is comparable. If both are wrong, we say that it is not comparable. Then if the set, if a relation S with a relation is a poset and every two elements of the set are comparable, then S is called totally ordered or linear ordered set. For example, for any set, for example, set of integers, okay, in the multiples of 3, 6, 9, 12, 15 and all, okay. So if every two elements can be compared, then we say that the whole set is an totally ordered or linearly ordered set. Okay, and this relation is called as an ordered or linear ordered relation. Okay, and a totally ordered set is also called a chain. Is also called a chain. We just call it as a set of numbers, a chain of numbers. Example, the partial ordered set of integers on a relation less than or equal to is totally ordered because every a less than or equal to b or b less than or equal to a for every two elements. Sorry? Yeah, it is or condition, not and condition. It is an or condition. So for every a and b integers.
If A equals 1, then B
Yeah, then b less than or equal to should be true. For example, if you take 2, 2 less than or equal to 2, okay, it is equal to 2. Then again 2 less than or equal to 2, it is equal. Okay, so either this should be true. Either it is equal or it is not equal, less than. Okay, less than or equal to for AB or BA for every two elements. For every two elements. For example, if you take 1 and 2, 1 is A, B is 2. Okay, 1 is less than 2, it is true. If you take, for example, uh, A as 2, B as 1. Two elements, A and B. It must be two elements, A and B. Okay, then we call it as an linear ordered chain. The same thing for Z plus in the division is not totally ordered because we have example of 5 and 7. This is the last one. لا لسه باقي بس شوية. خلاص مو مشكلة لا تقرأ. He looks very confused, huh?
Very.
Yes, they are very confused.
Even I think.
Problem is that that section has this starting from maximum and minimum relation. After two slides, what enumerate the relation.
Okay, that's good.
No, let me just finish this one and we'll take directly the question.
Not this question.
Let me just finish this one. Okay, we will take. Okay, talking about the hash diagram. In the hash diagram, we are going to remove all the vertices from the diagram. For example, if there is an if there are some loops, okay, and the directed vertices are removed from the hash diagram. Okay, hash diagram represent the partial ordering on a finite set using the hash diagram. The hash diagram says start with a directed graph for this relation. For any relation, for example, we take this example for the relation 1, 2, 3 on less than or equal to. We have 1 is less than or equal to 1, okay, and 1 is less than 2, 1 is less than 3, 1 is less than 4, and then 2 is less than or equal to, so 2 is equal to 2, 2 less than 3, and 2 less than 4, 3 is equal to 3, 3 less than 4, and 4 equals to 4. Now here the first thing in this is remove all the edges, okay, in the partial ordering because they are present in the edges and transitivity. Now for example, you have to remove the loops because it is already present here, okay, and here also we remove the loop, here also we remove all the loops. The next step is you remove all the directed relation because 1 to 2, this one is already present here, 1 to 2, so no need to include again 1 to 2, okay. Then 1 to 3 is already present from 1 to 2 and 2 to 3, so no need to have a loop or a extra way. Then 1 to 4 should be removed. Like this, 2 to 3 is already present and 2 to 4 is already through 3. Will be just the elements.
1, 2, 3, 4.
Yeah, that's it. This is called an hash diagram. Hash diagram for the partial ordering set. Or for example, the question may be like this for you. Let A is a set. Construct the hash diagram for the power set of A such that all the power set is a subset of power set of A. Now here, what are the power set you have? Power set A, B, C and A, B, C. Okay. Now first we have A, B, C. This is one subset of power set. Okay. Then we have A, B. We have A, C. And we have BC. This is 3 power sets. Null, we will take null also. These are 3. So you have these 3. Then we have A, B and C and null. So let us take A, B, C and null. Okay. Now A, B, C. Now C has a relation because there is a C element over here with this. Okay. Now here also there is a C, so it is having with this. Okay. Then here we have B, So B with the B. Here we have A with A.
And then, yeah, and B with BC.
B with BC. From where?
B
AC with BC.
and AB with AC.
Because you have A.
Yeah. And B with BC because it has B.
Now actually we are not going to look for every vertex. We are just going to look at directions. If you have repeated directions, we are not going to take it.
Okay.
Don't consider the repeated directions. See, you start with ABC.
Yeah.
Then you take AB, AC and BC.
Yeah.
Okay.
And
Now AB,
AB and
it has a relation with this one.
yeah.
Then this has a relation with this one and this has a relation with this one.
Yeah.
Right?
It must be just like
Yeah.
with BC.
A and B.
B with BC has a relation.
B with BC can go from this way.
Because B doesn't have a relation with AC.
No, we want to take from B to BC. So you can go in this way.
Yeah, we can go with
Okay. So
transitive.
yeah, we are not going to go every loop. We have here we have to minimize it. Okay. Now we start from ABC. Then we have AB, AC and BC. Now AB, AC and BC. Now if you want A to this one AB to BC, then you have here AB to from in this way. If you want from here to here, you have this way. You want to connect this A with from here, you have this way. Right? The next is A, B and C. The three. So B, we have a relation with B. We have relation with B. Okay. Now remaining with A and C. A, we have this one and C, we have this one. And null has with all through this point.
Also, they had a relation with AB, A comma B.
A comma B, it is going this way.
Yeah.
And C is going this way with B comma C. You have to draw the minimal diagram. First you take ABC. Okay. Now you have 3, that is AB, BC and AC. Okay. Now then you have A, B, C, 3. Okay. Now here you have A with A connected. Now this A, B with the B and C with the C. Okay. You have null. You have null.
A and B and C.
B and C. Okay.
B with AB.
No, it's not B with AB. Yeah, B with AB and B with BC.
And C with BC.
We don't have to write. See, we have to consider this power set. Based on the power set, you connect, you draw the graph such that there is no reflexive, there is no repetition, there is no symmetric, and there is no transitive. Okay, you just connect the vertices. Okay. Finally, the maximum and minimal elements of the set. Okay. Now here, this is the partial order set. This is what you have in the TMA to find the minimal and the maximal element. Now here from the given partial set on the divides of 2, 4, 5, 10, 12, 20, 25 on the relation divides, okay, uh, which are the maximal and which are the minimal elements. Now maximal elements, how do you draw this one? Based on the division. So you start with 2. We can divide 2 has a relation with 4, 12, 10 and 20. 10 and 20. So 2 has 10, 4, 4 from 4 to 12 and 2 have from 4 to 20. Right? Because 4 has a relation with 20. Yeah. 4 is also have relation with 2. Okay. The next is the 5. 5 has a relation with 10 and 10 with 20 and 5 has a relation with 25 in separate. Now here what are the maximal elements in this one? The maximum elements over here, the topmost element 20. Yeah, is 12, 20 and 5 for 5. Okay. So 12 is for 2 and for 4, 20 is for 5 and 2 and it is 25 for 5. Okay. Then minimal elements are the minimum one which is the divisors 2 and 5. Then the greatest element of the set, we say that A is the greatest element of the set, that is the partial order relation, if B relates with A for all B belongs to S. So we say the greatest element is B. The greatest element B relates with A when B is from A. I'm sorry, from the set. So the greatest element is unique when it exists, and then that element has a relation with all the elements. That element has a relation with all the elements, and also A is said to be the least element of the poset if A has a relation with B for all B belongs to S.
Can we just say, not have the manual related to all elements, just to the minimum element?
No, to all the elements. It's great.
Don't have related to.
No, we don't say the greatest 25. Not maximum. Maximum is different, greatest is different. Okay. Now here is an example. Determine whether the poset represented by each of the hash diagram in the figure has a greatest element and a least element. Now here in the A does not have any greatest element because there are 3 elements in the same frame. Yeah, and A is the least element because the only element which is the minimal, okay, has a related to all. Then B does not have greatest, does not have the least, okay, because there is A, B, and in the greatest you have D and E. So there is no single element in the B, and in the C you have the greatest as D, but minimal you don't have because there are 2 elements A and B. And D you have the greatest D and the minimal as A.
What about B? Minimal also.
Sorry?
B.
Where is B?
In.
No, B is not minimal. B in the level of B you have B and C. Okay.
He asking about this. So they have greatest and least.
No.
Don't have both.
Don't have both because there are two elements. If you take this diagram, there are 2 least and there are 2 greatest. So we don't have a greatest in this one. The next is talking about the upper bound and the least upper bound, lower bound, and the greatest lower bound. Okay, the upper bound for a set A is a subset of this the proper ordered set, S, and U is an element of S such that has a relation with U for all elements of A belongs to the set A, and U is called the upper bound of A, and the least is element X called the least of subset A if X is an upper bound that is less than every other upper bound of A, and from these upper bounds what you get U upper bounds. For example, in the upper bounds you have 10, which is the least one is the least upper bound, okay, and the lower bounds, for example, you have 20 lower bound. In this, the greatest lower bound, the maximum lower bound is calculated. Now if you take this example, the same example on this proper set on division, okay, find the lower and the upper bounds and also the greatest lower bound and the least upper bound. Now here the lower bound is 2, which is the minimal one, okay, and the upper bound is 4, 12 and 20, 4, 12 and 20, and the greatest lower bound, it is only 2. If you have more than one here, you calculate which is the maximum one, the greatest one, and the lowest upper bound is from this one. What is the lowest? 4. From this one, the least is 4. Okay, so this is what we have in this unit of M131 talking about the relation. Okay, I believe it's not easy. We don't have not much time. Anyhow, you have any question? The question on in the TMA. What is the question you had in the TMA?